with basic machine. A basic machine can be viewed as a function which maps the input set, let us say I, to the output set O. This function is known as a machine function. Mathematically, it is represented as machine function which maps input set I to the output O. For example, there are so many logical gates, let us say AND, OR, NOR, or number system, for example, decimal to binary converter. All this can be viewed as a basic machine. Let us take AND gate as a basic machine. We will see how AND gate will work as a basic machine. Since there is an input set I, so we are taking all the combination of 0 and 1 for an input. Since it is a binary, it works on the binary system. So input alphabet is just 0, 1. But we are taking the input in the form of pair because we know it takes two input. So the input is 0, 0. This is one input. Second input is 0, 1, 1, 0 and 1, 1. So total 4 inputs are there. Output is having only two symbols, 1, 0. So let us define the machine function for the AND gate which maps input set I to the output O, which is given by this tabular form. First row indicates input and second is output. So you can just see here for input, first three input 0, 0, 0, 1 and 1, 0, output is 0. And for input 1, 1, output is 1. So basic machine, it just simply takes the input and it gives the output. So user is unaware what is happening inside the machine. It is just black box for the user because we don't, like, user is not knowing how result is produced. It just gives the input and it gets the output. Okay. Yeah. Now we will see what do you mean by finite state machine. In automata theory, this is a first computing model and which is very basic computing model. Okay. So we will see what is FSM first. Actually, it is not like a basic machine, just give the input and produce the output. It is quite different. We will see. In FSM, we are concerned with machine behavior. Machine has internal state and on each state it receives input and it gives some intermediate result. Okay. So in FSM, there is some internal state and then we will see the final output. Already you have studied the state diagram in second year. So it is similar to that only. So here also you will find some state diagram and for each state there is an input and it gives the transition based on the input and what the output, right? So we will see how mathematically it is represented. It is represented using two functions. One is machine function and second is state transition function. First we understand these notations. I is the input set. S. Actually, S is a finite set of internal states of the machine. And O is a output. It is again finite set of output symbols. So how we define the machine function which maps input and state to the output, and how we define the state transition function which maps input and state to the next step. Okay. So mathematically there are this ways to define the FSM, machine function, state function. We also represent the FSM with the help of transition diagram. Or we can have the transition table or machine function table. So we will understand all this concept of FSM with one example. Yeah. So design FSM to construct a binary adder. So if we take the simply binary adder, it will be considered as basic machine. Just we are giving the input 0 comma 0, it gives the output 0, 0 1, it gives the output 1. But now we are going to construct the FSM, right? So here we are considering the binary adder with carry, and in this adder we are considering the state. There are two state, one is carry state and one is no carry state. So let us see how machine behaves on this different input, and how it moves from one state to another state, right? So input set is, since it is binary adder, so input alphabet is 1 comma 0, and here we are just combining we are taking the pair of this combination. We are considering 0 comma 0, 0 comma 1, all these are the input pairs. Yeah, output is again two symbols, 1 comma 0. Now here new term is that set of states, which is given by S. Since already I mentioned there are two state, that is carry and no carry. So here it is given two state, one is no carry and one is carry. Yeah, before just going to the actual designing, first we understand initially machine is always in no carry state, right? Because as we know there is no any input, and no addition will happen, so it remains in the no carry state. So initial state is very important, and as we know there is no this addition, so machine will be in the no carry state, right? But at any given time machine may resides in carry or no carry state. It depends on the result of previous addition. Let us take one example. We consider one scenario how it behaves. Yeah, we take just one random situation. Let us take current state of the machine is carry state, right? And we are giving the input 0 comma 0. Yeah. So how it behaves for this situation? Now the current state is carry and input is 0 0. Since current state is carry, so we need to consider one as a third input for this machine, because it is in carry state. So this first two bits are from this input only 0 comma 0. Why we are adding one more input, that is 1, because machine is in carry state, right? So addition will happen like this, 0 plus 1, and then it adds all these 3 bits. The result of this 3 bits is, yeah, output is 1, and since there is no carry produced from this addition, so machine moves to the next state, that is no carry state. So this must be clear, what is current state and what is current input. Based on that addition will be happen, and based on that decision will be taken. Yeah, let us move to this transition diagram. This transition diagram will clear actually complete behavior of this binary adder. First we understand the notations that we have used here. This circle is called the state. Yeah, there are two state which is labeled as no carry, and one is carry. We are distinguish this initial state from the state diagram. Initial state is always shown by this arrow. So you remember that initial state is shown by this arrow, and operation will start from the initial state only. This edges are called the transition, and this edges are labeled with some labels you can find here. This is called how we read this labels as, this is input and this is output, and this based on this input and out this it takes the transition. You can find for this first 3 input transition is to the same state, that is no carry. Again this is a transition from no carry. You can find the arrows here, right? So it means that this transition moves from no carry to carry. Yeah, you can see here arrow. Same, this is called the self. When the machine is in the carry state, and these are the inputs to the machine. For this input, machine remains in the same state, so it is showing by the self loop, right? And again this transition is going from carry to no carry. Yeah, let us see how it works, since it is initially no carry state. But you remember when we design the transition diagram, we are considering all inputs from each state. Okay, what happen when machine is in the no carry state, and we are going to consider all the inputs from this state. And once we have done all the inputs from this state, then we consider all the inputs from this state. Okay. So let us start with the initial state no carry. So no carry, it means that the third bit will be considered as 0, right? So you remember here addition of only not 2 bits. It will be taken third bit depending on the state. Yeah. So for input, we will take this input in detail. Input is 0, 0, and you can find we are considering this input from the state no carry. So third bit will be 0. So just read it as 0 plus 0 plus 0. So there are 3-bit addition. As we know, output is 0. And the result of this 3-bit, there is no carry. So that's why this transition moves to the same state. Okay. Similarly, you can find 0 plus 1 plus 0, 3-bit addition. Output is 1, but again there is no carry. So it remains in the same state. Again 1 plus 0 plus 1, same result, no carry. Output is 1 and it is in the same state. Yeah. Now the fourth input is remaining, that is 1, 1. So 1 plus 1 plus 0. So 3-bit addition, 1 plus 1 plus 0. So it means that output is 0 and carry is produced. So since carry is produced, so that state will be changed. So for this input 1, 1, machine is moving from no carry state to carry state, right? So once we have done with all the 4 inputs from this no carry state, we will switch to the carry state. Now from this we will consider again all 4 combinations. Now machine is in carry state means we need to consider third bit as a 1, right? So let's take all 4 input and see what is the result here. So input is 1, 1 and third bit is 1. So 1 plus 1 plus 1. So 3 bits are here. Output is 1 and yeah, carry is produced. So it is in state, right? Next, 0 plus 1 plus 1. You can find the output is 0. And there is a carry, so it switch to the same state. So like this for all 3 this input combination, output is these are the output and state remains same. Now machine is in carry state. You can find there is a transition for this input 0 plus 0 plus 1. The 3-bit addition will produce output 1 but no carry, so it goes to the same state.